So welcome everybody to this week's Heidelberg Joint Astronomical Colloquium. Last week we were looking into stars. Now we're going to very big objects, which nevertheless may be possible to physically model. Maybe you'll find out a little bit also from the observations, but that is going to be given by Anja von der Linden from Stony Brook, and I hand over to her host, Joachim Wamskans, to make the introduction.
Thanks. Yeah, it's my great pleasure to introduce today's speaker, the Heidelberg Joint Astronomical Colloquium Hijack, Anja von der Linden. Anja studied at Bonn University from 1998 to 2004. She did a diploma thesis already on a topic related to galaxy clusters. It was on the dark clump in a Bell 1942. Is it dark matter or a statistical fluke? Under Peter Schneider's guidance. She then moved to Munich, Garching, to the Max Planck Institute for Astrophysics, MBA, and worked on her PhD thesis with Simon White and Ginevra Kaufmann on galaxy evolution with SDSS. Then she, after finishing in 2007, she moved across the Atlantic to Stanford and worked at the KIPAC, the Kavli Institute for Particle Astrophysics and Cosmology, for 5 years, and mainly leading the project Weighing the Giants. Then she came back across the Atlantic in 2012 and worked at the Dark Cosmology Center in Copenhagen on a Sophie and Tycho Brahe fellowship jointly with KIPAC. And in 2015, she moved to Stony Brook University, where she started as an assistant professor. And 2 years ago, she was promoted to associate professor. And we are happy enough and lucky enough that she spends a sabbatical in Munich this summer so that we could get her cheap, sort of, and very happy to have her here. Thanks.
All right, can you hear me okay? All right, well, thank you for the introduction, and thank you for having me. Thank you for coming to my talk on this beautiful day. So I would like today to give an overview of how to do cosmology with indeed some of the largest structures in the universe, that is clusters of galaxies. And I was told that not everybody here works in cosmology. So I'm going to start with a very brief overview of observational cosmology today. In observational cosmology, we essentially have two sets of observations. One set of observations is our baby picture of the universe. That is observations of the cosmic microwave background, which originate roughly 400,000 years after the Big Bang. And everything else is essentially the local universe. I mean, yes, it goes back, to half the age of the universe or even more. But pretty much most of the other measurements, they measure the structure in the universe that we see today. That structure was not yet present in the cosmic microwave background. It's very smooth, although it has very tiny density fluctuations, which then grow into the structures that we see today. And even though these two sets of observations are very different, we have a very successful standard model of cosmology, which is able to describe both sets of observations with a model that only has 6 parameters, which is not a lot for such a wealth of data. That model includes general relativity as our model for gravity. It includes that the universe started in a Big Bang and was followed up with a period of exponential acceleration, that is inflation. It also generally just deals with structures on very large scales, where we assume the cosmological principle, that is homogeneity and isotropy. However, the model also requires the existence of dark matter and dark energy. Without dark matter, we wouldn't actually have structures like galaxies or stars or planets today. And dark energy is even more mysterious. What that describes is that after the period of inflation, the universe keeps expanding, but that expansion is slowed because of gravity. What we see, however, is that later in the universe, the expansion of the universe is accelerating, it's getting faster. This is akin to if you take an apple and you throw it up into the air, right? It's going to go up, but it's going to go slower. If you throw it really hard, right, it's going to leave Earth's orbit at some point, but it'll still get slower. And the universe is doing something similar, right? It expands, the expansion slows, but then what we see is that it's getting faster. This is like the apple starting to move faster away from Earth. So this is rather unexpected. And that latter part, we just described as dark energy, encapsulating that we don't really know what it is. Even though this model is very successful, it's also a bit embarrassing, because in the model, only 5% of the energy density of the universe is in a form of matter that we understand. So basically, we can describe it with the standard model of particle physics. And I'm going to count here stars, planets, gas, anything made of atoms. And by mass, it's mainly the baryons that matter. So colloquially, you usually describe cosmologists referring to the ordinary matter in the universe as just being baryons. But then most of the energy density in the universe is in these mysterious forms of dark matter and dark energy. Dark energy accounts for roughly 70% the energy density of the universe. So this is arguably one of the biggest questions in physics today. What is dark energy? What makes up most of the universe? And there's a few possibilities. The simplest one is that it's a cosmological constant, meaning it's one number. This is the one number in the 6-parameter model. That's the standard model in cosmology. This is lambda, and yes, this is the quantity that Einstein described as his biggest blunder. Having a cosmological constant means that we fix the equation of state of dark energy, that is the ratio between its pressure and density, to be exactly equal to -1 and to not be time variable. This is a good description of all data sets so far. None of them is believably 5 sigma away or so. But the problem with this is that there's really no satisfying theoretical explanation. So naturally, we're also looking at other models. And so one of the possibilities is that the equation of state is actually not exactly equal to -1, or is even time variable. Another possibility is that gravity is actually not general relativity on large scales, and this will fall under the term modified gravity. But because this plays such a big role in cosmology, precision measurements of the equation of state, dark energy, that is this W parameter, are the goal of many cosmology experiments. We've recently seen the launch of Euclid, and so measurements of W are exactly one of the main goals of Euclid. And then the other part is dark matter. Dark matter drives the formation of structure in the universe. Otherwise, the tiny density fluctuations that we see in the CMB would not have had time to grow into the structures that we observe today. Our observations are mostly well described by dark matter being cold. That means it's non-relativistic today, and being collisionless. So another question of the fundamental nature of our universe is, what is the particle nature of dark matter? And I also put on this slide, what is the mass of neutrinos? Well, we do know that neutrinos exist. They are part of the standard model of particle physics, except they are massless. However, from neutrino oscillation experiments, we do know that neutrinos have a minimum mass. We know that the sum of the neutrino masses is at least 0.056 eV. And cosmology is actually interesting here, because if neutrinos are very massive, they also change the growth of structure. And so cosmology can place an upper limit on the sum of the neutrino masses, or in combination with oscillation experiments, actually measure its value. All right, so there's a few symbols that you're going to see in this talk. I mentioned that many of the more local observations measure the structure in the universe today, and and some measurements, including galaxy clusters, are best at measuring the 2 parameters that are the matter density and this funny thing called sigma-8. Where the matter density, this is the total energy density of cold dark matter and of baryonic matter. Sigma-8 then is, nominally it's the amplitude of the power spectrum measured at 8 megaparsecs. If you haven't heard of it, the way to imagine is that you take the universe and you take really large ice cream scoops of the size of 8 megaparsecs. And then you scoop out a bunch of ice cream scoops of the universe, and you might just measure the standard deviation of how much mass is contained in them, right? So that gives you a sigma, and you've measured it on 8 megaparsecs. So this tells you how smooth or how structured the matter distribution is, right? And so when you see plots where we show sigma 8 versus omega matter, whether that's cosmic shear, whether that's clusters, what they've done is we fixed 4 of the 6 parameters, because we know what they are from CMB, and we free up these 2 and we constrain them. All right, so that's the 6 parameter model. So in that case, the standard model we usually call flat lambda CDM. That means we fix the sum of matter density and dark energy density to be exactly equal to 1. That means the universe is flat. We fix dark energy to be W equals -1. That is, we have a cosmological constant. But of course, we also want to learn about some of the other things. Maybe the universe is more complicated than the 6 parameter model. Maybe it's a 7 parameter model. And so then we have a few options. One of the options is we free up the neutrino masses as the 7th parameter. Then we call it flat neutrino lambda CDM. Or we free up the dark energy equation of state. So then this would be the 7th parameter, and we measure that. We can also free up additional parameters. We can free up neutrino mass and W at the same time, or we even allow for time evolution of the dark energy equation of state. But each time you see one of these additional parameters, we freed up another parameter in the cosmological model. So flat lambda CDM works great. Are we beginning to see cracks? Yes, and it's become quite exciting to see some evidence that flat lambda CDM is not the entire story. Observations by the Planck satellite of the CMB are fully consistent with flat lambda CDM. So some of the evidence that there's something else to the story comes from other probes, from local structure probes. The biggest tension today is the Hubble constant, and I'm not going to talk about it. But there's another tension, and that's called the S8 tension. And this is essentially based on cosmic shear, which does come from the gravitational lensing community. In cosmic shear, we measure the correlation function of the shapes of galaxies, where the shapes are sheared by the matter distribution. And this is also a very sensitive local structure probe. And so in the parameter space of sigma 8 to omega matter, what we see is that the 3 largest cosmic shear surveys, they all fall along these bananas, which are approximately 2 signal away from Planck when you extrapolate Planck to sigma 8 and omega matter today. So none of them itself is super significant, but they all kind of measure the same thing. And they call this the S8 tension because if you reparameterize sigma 8 and omega matter to S8, things look less banana shaped. So that's an interesting evidence, but it remains to be seen whether this is actually significant. So now I'm going to talk about where clusters come in. This movie is a standard n-body simulations, how structure evolves in the universe. It starts pretty flat, and then under the influence of gravity, matter collapses into filaments and then into massive halos. And I asked let me play this again. And I asked my simulator friends to draw little circles around halos each time they pass a certain mass threshold. And in the top left, we're going to keep count of how many halos of a given mass we have. And this function is the halo mass function. And as time evolves in the universe, you also see the halo mass function evolve. And so our goal is to measure the halo mass function and its evolution of time, because that halo mass function and its evolution, they're actually very sensitive to how you set up these simulations. If you add more dark matter, then structures are going to go faster. That means that the halo mass function is going to evolve faster. If you add more dark energy drives things apart, and that means the halo mass function is going to evolve slower. If you change the laws of gravity, or you add different kinds of dark matter, including neutrinos, you can change the shape of the halo mass function. So the measurements of the halo mass function are also sensitive to the type of dark matter. And this is a very sensitive cosmological test because it probes both the growth of structure immediately, but it is also a measurement of the geometry of the universe. And what I mean by that is supernovae are one of the most famous cosmology probes. And supernovae are a geometry measurement. They measure distances. And the distance is a one-dimensional thing. Clusters, or really the halo mass function, is also a geometric measure because I'm counting the number of halos in the volume. So I actually get a three-dimensional measurement of the universe. And this is the other explanation of why the halo mass function is actually very sensitive to most cosmological parameters. All right, so I have halos in the simulations, but I'm an observer. And I don't observe halos on the sky, I observe clusters. The halos that are cosmologically most constraining are the most massive ones. And so we identify those as galaxy clusters on the sky. So just briefly, these are very massive, generally things which are over 10 to the 14 solar masses. They're mainly dark matter, above 80%, but they also have about 10% hot gas. And this is important. And only about 2% of their mass is in the form of galaxies. Most of these are red. And at the center, there's a really large red galaxy, right? Good. Currently, the cluster samples that we use for cosmology of the order of a few hundreds to a few thousands. But we're very close to having much larger cluster samples from many sky surveys, which will identify clusters by the hot gas content or by the galaxy contents. And so there's tremendous statistical potential in doing cluster cosmology. And well, I guess 8 years ago, this was recognized in the Cosmic Visions report, which concluded that the number of massive galaxy clusters could emerge as the most powerful cosmological probe if the masses of the clusters can be accurately measured. And of course, that if statement is what makes cluster cosmology really hard. All right, so this is the outline for the rest of the talk. I'm going to talk about how to do cluster cosmology in practice, why the mass calibration is difficult. I'm going to comment on some of the current results. And in the end, I hope to have a little bit of time to also tell you about where we're at with the Rubin Observatory, the LSST survey. Okay, so to do cluster cosmology then, we need predictions for the halo mass function from simulations. I showed you an example. We need to go out and find our clusters, and we can do that in different methods. And then we need a way of tying together the mass of the halo sets in the simulations and whatever observable I used to identify the clusters. And you can already tell this relation is not straightforward. It's mostly a statistical description because every cluster is going to scatter away from the mean. To find clusters, we do best by picking them up by the baryonic content. Remember, I said about 10% of the mass in clusters is in the form of hot gas. That gas is so hot that it shines in X-rays via thermal Bremsstrahlung. And so if we see extended X-ray emission, we can be pretty sure that that's a cluster in the extragalactic sky. That same gas also causes inverse Compton scattering of CMB photons. So every massive cluster is going to leave a little shadow on CMB observations. So these both are methods of identifying clusters via the hot gas content. But we are really good at finding galaxies too. And so we can also use the galaxy population to identify clusters by looking at overdensities of galaxies. Okay, good. So I found a bunch of clusters. I then need to measure their masses. None of the ways by which we identify clusters actually gives us the mass, right? We can measure number of galaxies. That's not the mass. I can measure an X-ray luminosity. That's not the mass. I can measure an NC decrement. That's not the mass either. They all correlate with mass in the sense that if one cluster is twice as X-ray bright than the other, it's probably more massive too. However, that relation has considerable scatter of the order of 20 to 40%, depending on which observable we're talking about. So then, is it necessary to precisely measure the mass of every cluster in the survey? It used to be that cluster cosmologists used to do that, but we've moved away from that. And so now we're more towards doing things statistically. And so all we need to know is how to describe the population. So ultimately, what's the probability of finding someone observable given the halo mass that corresponds to the simulations? The simplest assumption here is that the mean of the observable, doesn't matter which one, follows a power law relation with mass. So in log-log, that's a straight line. Looks easy, right? All right. However, there's an intrinsic scatter around that relation, which is log normal. And so then to forward model my cluster population, I go to the line, and at every given location in mass, I scatter clusters up and down according to the intrinsic scatter of 20 to 40%, right? So we spread out the population in the observable. And then every method of identifying clusters will always say, I'm going to count clusters above some threshold, say 20 galaxies, or X-ray luminosity above some threshold, or SE decrement above some threshold. And that means I only observe that part of the population, which is colored in blue, and I don't see the orange halos. In the observations, of course, we don't have the x-axis. We only have the y-axis, and that means all that we can do is draw a histogram of how many clusters we have in each bin of observable. And so in any bin that you look at, what you have is that you have a few clusters which actually scatter down from the relation. You have some clusters which are on the mean of the relation, but mostly you have clusters which are scattered up. All right, most of the clusters that we see have scattered up from, the mean relation to they just scatter high. It can be 1 sigma outlier, or it can be 5 sigma outlier. Okay, so we have this histogram. How do we go back to this relation, which is essential for doing cluster cosmology? That is, how to relate the mass of halos in the simulations to what we have observed on the sky. Well, we need to go and actually measure cluster masses. There's a few methods to do that. You can use X-rays. There's some issues with assuming hydrostatic equilibrium. You can use galaxy dynamics. This has both large scatter and bias. So the method that's now established as the best choice is using weak gravitational lensing. That still has considerable scatter. However, on average, the bias is pretty small. Okay, so if you average over enough clusters, the lensing signal is going to be accurate. And very brief, what I mean by weak lensing is, so we're going to go back to general relativity, and we're going to use the fact that mass deflects light. So we're going to measure the light deflection to estimate the cluster mass. But we're not working in the strong lensing regime here. So the simple picture of lensing is, imagine I have some background galaxies, and life would be really simple if they were all round. I add a very massive object in front, then the objects right behind, say this cluster lens, we're going to see multiple images, we're going to see arcs. Beautiful. If I go further away from the center object, the background objects are not multiply imaged. However, they are distorted. Okay, each of these objects is now tangentially aligned with respect to the direction of the cluster. So galaxies around this would be simple. However, they're not. Intrinsically, they're basically elliptical, and so the true background might look like this. And then once you lens it, in the weak lensing regime, you cannot tell by looking at an individual galaxy whether that shape is because of gravitational shear or because of its intrinsic shape. Strong lensing is great, and it gives us these really pretty images, but strong lensing only measures the mass on the core of the cluster. We need to measure the entire mass of the cluster, which is much further out here, and this is why we have to resort to weak lensing. And we're going to just do this statistically by looking at many galaxies. You can recover that tangential alignment. To give you an idea of the scale, here's the baby bullet cluster and its Hubble image. The entire Hubble image fits into this white box, but the larger image is the ground-based data. And we're going to measure weak lensing between these two yellow circles, right? So we're away from all the pretty and really interesting stuff. Okay, then to infer a mass based on these measurements, we need to measure the tangential alignment. We also need to have some idea of the redshifts of the galaxies for which we measure the shapes. And so these are two measurements which illustrate that. In the top panel, this shows the average tangential alignment of galaxies as a function of distance to the cluster center. And so you see, as you get closer to the cluster center, that average alignment increases, right? Because we get stronger, we get closer to the strong lensing regime. Alternatively, I can bin my galaxies not by distance, but by redshift. And so this cluster is at this redshift. The galaxies in front of the cluster, the average alignment is 0, which is a good cross-check. And then behind the cluster, the shear increases according to a geometric function. In the end, I also need to make some assumption on the mass distribution. So usually we fit a spherical NFW model to the observed shear signal. And these are the 3 ingredients. And much of cluster cosmology today is ultimately limited by how well we can do in each of these 3 areas. Whereas right now, number 2 and 3 are the dominant contributors. Okay, great. Am I done? So lensing masses still have intrinsic scatter of 20% or so, which means they're not great for individual clusters. But if I have an ensemble, then the average mass is nearly unbiased. Okay, there's a lot hidden in the nearly, but for the purpose of this talk, let's assume they are unbiased. Okay, good. So I can go to all the clusters in a given bin. I'm going to measure the lensing mass, and that gives me an accurate measure of the mean mass in that bin. Well, that gives me the red points. Okay, that means I still have not recovered what the mean relation between mass and observable is, just because of, well, this plot that I drew. So lensing masses alone are not enough. We need additional information, or we actually have to fix, say the slope and the scatter of this relation. To fully describe this relation, I need 3 numbers. I need the slope, I need an intercept, and I need the scatter. Right? So if I assume 2 of these, I can measure the 3rd. However, ideally, I would like to have more information to constrain the slope. And so what is helpful here is if you have an extra mass proxy. Okay, so an extra measurement. We found clusters, that is, we have 1 observable already, say X-ray flux, and we have the lensing masses. Those are not enough. There are some observables which are extra valuable, and those are low scatter mass proxies derived from X-rays. So there are some quantities, such as the temperature of the gas, the total mass contained in the gas, or the product of the 2, which have a much smaller scatter with the halo mass than the other observables, less than 10%. So if I have access to those for even a subsample of my clusters, say for all of the ones in red, I can measure their relative mass. None of these gives me the absolute mass, okay? But I can say, okay, this cluster is twice as massive as the other one. And then lensing comes in to determine the unknown factor, which is the absolute mass calibration. And so by utilizing these 2 measurements at the same time, we can constrain the mass observable relation and to cosmology with it. Should I pause for questions at this point? All good? All right, please feel free to ask questions. Okay, so Joachim mentioned that a while ago I worked on weighing the giants. It's 10 years old now, which makes me feel old. But back in the 2000s, we didn't have dark energy survey or KITS, or let alone Euclid. So to do weak lensing of these clusters, we had to go and observe them 1 by 1. And we did this with the Subaru telescope, with the old camera, with the prime cam. So we gathered lensing observations for about 50 clusters. This is a subsample of only about 200 clusters collected from the ROSAT all-state survey, which flew in the 90s. So this is fairly old data. So for these clusters, we have really nice weak lensing imaging. We also have Chandra X-ray observations for these low scatter mass proxies. Right, and so there's a bunch of people involved in this. 5 main papers from about 10 years ago. So weighing the giants was the first time that we used weak lensing self-consistently for cluster cosmology. But the other innovative part, and the other part which makes it, I think, first experiment that does modern day cluster cosmology, is the use of hierarchical modeling. And what I mean by that is, yes, I showed you a histogram, but we're not using histograms, okay? In the way that we do cluster cosmology, every cluster enters the likelihood individually. It's a Poisson likelihood. So every cluster has a latent parameter of true mass. It has its individual weak lensing mass. It has its individual survey observable, and there's available follow-up mass proxy. And so in this model, the parameters that describe the scaling relation, slope, intercept, and scatter, they become hyperparameters in the sense that if I draw the scaling relation, right, I'm just writing out, okay, the probability to scatter up and down given the mean relation. And what we do is that we make these three parameters part of the MC-MC chain. We vary the parameters that describe the prior at the same time as we vary everything else. So in stats language, that means the scaling relation parameters and cosmology become hyperparameters to describe the population. And so that means we simultaneously solve for the scaling relation and for cosmology. That approach was first developed by my colleague Adam Mans in 2010. Weighing the Giants ultimately added the lensing part to it, but there's now becoming more of an industry where we see similar works being done for SE-selected clusters, as well as the Rosetta survey. Here's the same thing in pictures. We use prediction of the halo mass function, our cluster sample, other mass proxies plus weak lensing, outcomes, cosmology, and scaling relations. And so here is an actual mass observable relation from Weighing the Giants, where we plot mass of the cluster and the X-ray luminosity. So the gray points, that's our data, and the green band, that's the best fit mean relation. And look at it, most clusters have indeed scattered. All right, this is my slide from November. This is an assortment. These are the results from gas-selected clusters, that is X-ray or C-selected clusters using hierarchical modeling in relation to the Planck measurements of sigma 8 and omega matter. And so really what you see is, well, they're all kind of in agreement with Planck. They don't really weigh in on the SA tension. But 2024 has been really interesting because we've seen two new results. One from January is an analysis or reanalysis of more clusters from the South Pole telescope. So these are selected via the SC signature. And they've broken the 1,000 cluster barrier. So SC has moved from this constraint to these red constraints, and they agree perfectly well with Planck. In this case, they're not actually using a low scatter mass proxy, but they are still using an additional mass proxy, which is optical richness. So the data set here is the SC, the CMB observations, the cluster counts there, plus they use optical data from dark energy survey. And they use the dark energy survey data both for the weak lensing, as well as to get an additional mass proxy, that is the number of galaxies in a cluster. And then a few weeks later, the German half of Rosetta, they published their first cosmology analysis, and we've now broken the 5,000 cluster barrier. So this has been a remarkable jump, I would say. And the analysis is actually very similar to the SPT one. We use X-ray selected clusters in half of the sky selected by the Rosetta X-ray telescope, and combine these with optical data from DES to get weak lensing masses, as well as optical richness. And so these new constructs, the Rosetta constructs, are the yellow ones. And you see neither SPT nor Rosetta falls along the DS8 tension that the cosmic shear surveys find, even though they use the same optical data. Okay, so right now, cluster samples selected by the hot gas content, they do not support DS8 tension. Okay, but we want to measure dark energy. Clusters today deliver some of the tightest single probe constraints on W. Planck, well, CMB is not great at measuring W because Planck is just very early in the universe. There's no dark energy yet. Weighing the Giants for a long time was the tightest limit on W, but we now have the Rosetta results, and I also added the recent results from DESI. And so you see actually that these are very similar in constraining space. Now, DESI, if you follow cosmology a bit, DESI made headlines by finding evidence that that there might be evolving dark energy. And so that's this plot where, if we're here, we have flat lambda CDM. DESI alone, that's the dashed contours here, finds marginal evidence away from that. They combine with supernovae to have of the order of 2 to 3 sigma significance. And I've simply compared it to, well, actually weighing the giants. Okay, these colors are a bit funny on the projector. But weighing the giants would be the purple constraints compared to the DESI constraints, and actually very similar. Okay, small differences in terms of for DESI. The standard model is not quite within the 1 sigma contours. For us it is, but yeah. Then there's also results in neutrino masses, in particular Rosetta with 5,000 clusters, and going down to relatively low masses is able to place a relatively tight limit on upper limit on the mass of neutrinos. And then combined with oscillation experiments, we can actually claim to have a measurement. All right. Okay. So what I talked about until now is cluster cosmology with gas selected clusters and using a hierarchical modeling approach. But we can also do cluster cosmology with optical surveys. And so I will mainly talk about the results from the dark energy survey here. The dark energy survey covers about 5,000 square degrees in the south, and it has delivered competitive cosmology using various 2-point statistics. And most notably, these galaxy catalogs are also used for the SPT and Rosetta weak lensing mass calibration. The cluster cosmology analysis done by DES is quite different from the hierarchical model. So here we find clusters by the red sequence, namely by overdensities of red galaxies, with about 6,000 clusters. But now we bin the data. This shows the binned weak lensing signal in bins according to richness as well as redshift. And so we see in each of these bins, we see these beautiful stacked weak lensing profiles going out to, well, actually several tens of megaparsecs. So this is much larger scales than what we measured in weighing the giants. And so we take these data and we fit a mean mass to these, which means that for every bin in richness, I can say at a given richness, what is the average mass of the sample? And we get a line like this. Now, this is, here the axes are reversed from what I showed you. Okay, I can always go and say, okay, in a given richness bin, what's the average mass? There's nothing wrong with that, but it's really hard to invert this plot, because for that I would need to know what the scatter is. All right, and so we've done cosmology with these. I will guide your eye. Blue contours are Planck primary CMB. Red contours are various 2-point statistics from the dark energy survey. Gold are X-ray selected surveys, X-ray selected clusters from weighing the giants. Pink is Z selected clusters from SPT. And by now you've probably spotted the gray elephant in the room, which is that. These are the results from optically selected clusters in DES. These contours are 5 sigma away from Planck at low omega matter. All right, so that's a bit strange, given that I just told you how great cluster cosmology works. So something's happening here. So what's going on? Well, it's unlikely that the standard cosmological model is this wrong, right? It's also unlikely that the DES weak lensing shear and photo Z measurements are this wrong, right? I mean, they do fine with 3x2 point, they do fine with the Rosetta and SPT clusters. But it's more likely that our model that goes from the halo mass to the cluster observables, in this case richness and weak lensing, is incomplete. And I should say the DS collaboration did a really tremendous effort after unblinding in trying to understand what went wrong. However, the constraints moved from gray to red, so it didn't really fix the tension. But also they published this, right? And I think this is really noteworthy. I think it takes a lot of courage to publish a result which is 5 sigma away. So I think there's a lot that can be learned here. Okay, DS is not the only experiment. Also, there are other flavors of the DS analysis. So the DS nominal results are the gray ones. If we take a cluster sample from DES that has a higher threshold in terms of the number of galaxies, we get the purple constraint. So things move towards Planck. This tells us that it's something about the clusters with low richnesses. We did a previous analysis on SDSS, which uses the same code, large contours, consistent with Planck. And there's an independent analysis of the KITS team. And they do some things differently. In particular, they look for clusters not just as overdensity of red galaxies, but they look in photo Z space in the code developed by Matteo. Much of the modeling is the same, but what I find interesting is that they use only the small scale lensing signal. So they don't try to model the signal out to 10 megaparsecs, but stop at 3. By now, it has become clear that the missing link between our modeling of halo mass to cluster observable is related to the shapes of clusters and projection effects. We actually know from simulations that clusters look like this, right? They are elongated, they have substructures, and they have filaments feeding into them. And everybody so far is being a good physicist and just models clusters as spherical cows, and these are not the same. And so we have to consider what particularly the ellipticity of clusters does to observations. So the next step away from the spherical cow is that I assume that it's an elliptical cow, right? And so if I have my elliptical cow, and I'm going to call it a American football-shaped halo. So if the football is aligned along line of sight, that means that the projected surface density is higher, and that will bias the lensing signal high. It will also bias the number of galaxies within a given aperture high. To a lesser degree, this also causes the Z measurement to be high. If the football-shaped halo is within the plane of the sky, all of these quantities are underestimated compared to the spherical case. In addition to that, when I have my elliptical cluster, I also know that the filaments predominantly feed into that halo along the major axes. Okay, so if I look at this cluster through the cylinder, I get the mass not just from the main halo, but also everything that's projected along the sky. The alignment is not perfect. They're not all in straight lines as I drew, but there's some opening angle away from that. And there's been lots of work on trying to understand what this does to the DS selection. And people have shown in simulations that the red mapper selection does tend to predominantly identify clusters which are aligned along line of sight. And that orientation effects will bias high both the lensing signal and the richness signal at all scales, so at any distance away from the cluster. I'm going to skip this part. So all of that work is based on simulations right now. But in my group, we've been asking, can we learn the halo orientation of real clusters in the data? Is there something that can tell us whether a cluster is oriented along the line of sight or in the plane of the sky? And so we've been using the shape of the central galaxy of clusters as a tracer. And I'm going to call these brightest cluster galaxies, but really they are the central galaxies. And my simple model is that if I have a large elliptical halo, the BCG is a small copy of that, and it has the same shape, right? So if I have an elongation going this way, the BCG will follow that. It'll just be a bit smaller. And of course, the main halo is composed of dark matter, which I cannot see, but I can see the stars in the BCG. So then, if I have the football-shaped halo, that is, I have the football-shaped BCG, if I orient that to be along the line of sight, I'm going to observe it to be round. My expectation is that if I see a cluster with a round BCG, that cluster, that halo, is aligned along line of sight. Vice versa, those clusters with the most elliptical BCGs are most likely to be oriented in the plane of the sky. And so we've shown on weighing the giants data that BCG ellipticity actually is a good predictor of the bias in weak lensing mass. So this is a plot of weak lensing mass divided by true mass as a function of axis ratio of the BCG. And so we see that for the clusters with the roundest BCGs, the lensing mass is actually 20% higher. And those with the most elliptical BCGs, the lensing signal is about 20% lower. So we actually do really good at predicting the intrinsic scatter in weak lensing. Not perfect, but also the assumption is not really perfect. So we're then trying to do the same in DES data. But up until recently, we did not have the X-ray selection for DES data. So we're working with the C-selected clusters. And what we've been able to show so far is that clusters with round BCGs indeed have richnesses which are 10% higher than those of elliptical BCGs. So that also means that if I go and select clusters by richness instead of SC signal, I'm more likely to select clusters which have round BCGs because they get a +10 in richness. We've looked at the lensing profiles, and we see distinctions between the samples that have round BCGs and elliptical BCGs. We see this both in ACT and SPT. We also see this in the galaxy density profile. However, it's the exact opposite of what simulations predict. So right now we've been puzzling over why our observations look exactly the other way than if I look at halos selected by mass in simulations. And of course, our process is very different. However, right now, it looks like that the shape of the BCG does not trace only the orientation of the halo, but also something else. So possibly something that's related to the dynamical state. All right, can I talk about Rubin a little bit? Okay, good. So I mentioned that cluster cosmology is getting really exciting. So we've had 5,000 clusters from Rosita already, but there are many surveys that have started or are about to start soon. And so to me, given that cluster cosmology is so fundamentally multi-wavelength endeavor, we're selecting X-rays for SC, we need optical for masses and richnesses. I think the coming decade or so will be super exciting. What I'm most involved in is the Rubin Observatory with the LSST, the Rubin Observatory with the LSST survey. This is an 8-meter telescope, basically done in Chile, with the largest digital camera ever built, 3.2 billion pixels. It's located on Cerro Fortune in Chile. And starting late next year, it's going to start conducting the legacy survey of space and time, a 10-year survey of the entire southern sky. The science drivers it actually has many science drivers. One of them is cosmology. Another really big one is to explore the transient sky, as well as the solar system, and to map the Milky Way. These science drivers, they lead to a survey design, which means that LSST is going to take many really brief exposures, 2 times 15 seconds. It goes to a given place on the sky, takes an image, moves to the next one. It has the capability with this strategy to emit the entire visible sky, night sky at a given point every 3 nights. It's going to do something like that, not exactly. And it's going to keep doing that for 10 years. So one is going to build up a 10-year movie of everything that changes. But also over these 10 years, it's going to build up a really deep and really wide image of everything in the southern sky to weak lensing quality imaging in 6 bands. And every visit is going to lead to the order of 10,000 alerts per visit. And I know that there's many people in RE interested in that aspect. I wanted to show you a little bit where we're at. This movie is 1.5 years old. There's no mirror in the telescope mount assembly yet. But this is a telescope which will hold an 8-meter mirror, and this is a real-time movie. It was really fast. Okay, compared to VLT, it's much faster. You'll also say it's really short. It has a focal ratio of 1.2, and that is to enable that really wide field imaging, right, the 10 square degrees. And it has to pass so that if there's a trigger, it just moves to the other part of the sky, and it settles in time of less than a second. We have news from 2 weeks ago that the mirror, which was actually the first thing that was constructed, I think 2008 or so, is now no longer just a piece of glass, but it's actually a mirror. So this is the first time now that has been coded. It looks a bit weird, and that's because to make the telescope this short, they've made the tertiary mirror part of the same glass as the primary mirror. Okay, so the aperture of LHC is actually quite obstructed. Only this outer part is the primary mirror, it's the secondary mirror, and inside that is the camera, and then this is the tertiary mirror. And we're getting close to having actual data. There's a website, if you just Google LSST schedule, you get to this webpage, and it has a bunch of milestones. We've done the coding. Right about now, the camera is on its way to Chile. This will be the next milestone. But also, later this year, July, August, September, we're going to be observing with Rubin for the first time. There's a separate camera, which is the commissioning camera, which has a smaller field of view. And commissioning really is meant to do engineering things, such as the active optics system. Although we're, of course, hoping that there will be some science quality data. Right, and then ComCam comes off the telescope, large camera LSST cam gets installed. It has a first photon and a first light, which I find really confusing. What first photon means, first sky photon. First light means we can now routinely acquire science-grade imaging. And next year, we're going to spend some time on science validation surveys. And the main survey is expected to start in the second half of next year. So we're getting close to data. The first really interesting release will be data release 1 that encompasses the first 6 months. However, the project is taking another 6 months to really finalize the processing. And so 12 months after the start of the main survey, there will be the first data release available to those people with data rights. The science that I want to do with it, of course, comes back to galaxy clusters. The cosmology aspect of Rubin is organized in the Dark Energy Science Collaboration, which has over 1,000 members. So we basically have to organize and figure out how to do cosmology with LSST. We're going to do that with 6 probes. One of them is galaxy clusters. And so, yes, we can do cluster finding with the LSST data, but we can also confirm cluster candidates identified in X-rays or in a C. We can measure great weak lensing masses. And ultimately, utilizing all of these, we plan to do cluster cosmology. So for me, LSST promises to be weighing the giants-like lensing data for all the clusters in the southern sky, and that's pretty exciting. LSST has a lot of synergies with many other experiments. Most obvious, the other cluster survey. So if we think of clusters selected by X-rays or LC, LSST can provide cluster confirmation from redshifts and weak lensing masses, at least for clusters at redshifts less than 1. And so these will be much deeper and higher signal to noise than the masses that we currently get from DES. That means if we can make the modeling computation tractable, we can actually do more detailed analysis than currently possible. It also has a lot of synergies with the space-based experiments, including Euclid and Roman. Both Euclid and Roman need ground-based imaging to do photosys, and of course, they both really would like to have LSST for that. So right now, the assumption is that we will get a combination for the photosys. What is interesting to me is that the combination with space-based imaging will also help LSST significantly in terms of deblending and weak lensing shape measurement. And this is my summary. Clusters are a very powerful probe of cosmology. Many aspects are challenging, but with hierarchical forward modeling and multi-wavelength data, we can in principle do really well. We're going to have lots of exciting new data coming soon. Okay, thank you.
So thank you very much, Anja. That's fantastic insight, I thought, to what's going on right now in this field. Thank you so much for that. We have an online audience and we have an audience here. I'm sure there are questions. I would like to start with the audience here. there's one.
Thank you very much for the talk. In your opinion, looking at the Eurosita results, do you think that in the analysis something should be done differently, or some different approach? Or
I think they did a remarkable job, given the amount of data and the little time that they had. Right? I mean, they had time pressure to publish these results, and so in general, I think they've done everything right. The basic methodology is the same as running the giants, is the same as SPT, and the hierarchical modeling, in principle, actually gives you a lot of freedom, because as long as you capture things like the correlation coefficients in the observables, the things I talked about for the optical surveys, they're already self-consistently absorbed, and so that itself is very powerful. I think there's always details that you could do differently. I think there are lots of indications for things that are interesting. I was most surprised that the Eurosita model has a very large intrinsic scatter. So in running the giants, we had a scatter of about 40% in X-ray luminosity compared to mass. Eurosita doesn't use X-ray luminosity as a tracer; it uses count rate, which is somewhat different, but they have a scatter of 100%. And so to me, that sounds like we can actually become more ambitious in trying to constrain more complicated models of the scaling relation, right? So this would be a first. Everybody else, does the power law, and yes, there's prescription there for, say, redshift evolution. But I think in this case, there actually is enough data to constrain things like, is there a mass dependence of the scatter? That so far has not been necessary for SPT or so, but I think I'm trying to move them towards we should look at more complicated models of the scaling relation.
I don't see questions in the hall. If there are some online, please just type a message that you'd like to ask a question. I have a question. You mentioned the optical proxies. Could you give us some idea about, and presumably most of these clusters don't have full spectroscopic coverage in the optical. If you would have that, would that be useful to you? Would it make a big difference? Of course, it's very expensive to do. And I know that there's sort of discussions going on to what extent we want spectroscopic coverage. So maybe you could comment on this.
Yes, spectroscopic coverage would be great. I don't think it's going to fundamentally change anything. You could say use velocity dispersions as an additional mass proxy. They're similar to wig lensing. However, we've seen from trials and simulations that both the scatter and the bias in, say, these various masses are much greater than for wig lensing. So I don't think that it can replace that. However, what it would tell us is the cluster membership. So in terms of optical proxies, we basically count the number of galaxies. But in terms of, I talked a little bit about orientation and projection effects. So we know that some of the red galaxies that RedMapper selects are actually not within the halo. Yeah. They're actually along the line of sight.
Yeah.
So that's something that people are looking at.
So these sort of infalling galaxies into the cluster, so to say, you get a spectroscopic signature of that.
Right, exactly. So if we can tell apart, so these galaxies, I drew them in blue, I should have drawn them in red. But if the galaxies in these halos, they're going to have the same color as those in the main halo. But spectroscopy would actually be able to tell us to some degree whether the galaxies we see here are part of the main halo or are part of the infalling structure. That's one of the avenues where spectroscopy would be very helpful.
Right, and how deep do you actually have to go? The question, I'm getting a bit technical here, right? But you've got a range of masses of galaxies in these clusters. How deep do you actually have to go? If I want to design a spectroscopic survey, what would you say is the minimum requirement?
So RedMapper counts red galaxies above, I think, 0.5 L star. The magnitude that corresponds to is going to depend on the redshift. But if Yeah, if we are at a redshift of 0.5, then you would need to go down to 23, so that would be too expensive. But
All
you
right.
could learn from the more nearby clusters.
Okay, right. Joachim.
Thanks. I have a general question. On your second slide, I think the first on cosmology, you listed cosmological constant and varying. Next one. Yeah, right here. For the cosmological constant, you had the fourth bullet, no satisfying theoretical explanation. You did not put this statement under time-varying scalar field nor modified gravity. Is this on purpose?
Well, this is basically what the theorists tell me. Right, so, I asked them, well, why are we not happy with the cosmological constant? And they're just not happy with them. With this, because I think my understanding is that there's a lot more models and theories that you can fit into these two categories than that one. But if there's a theorist in the audience, then by all means they should speak up.
Okay, we're a little bit running beyond time. If I may, I'd like to ask a very naive question. I mean, with something like LSST, you're doing a photometric survey, go very, very deep. Is there going to be any point where you can use weak lensing to identify mass structures that you don't have to go to the proxies? And is that an important factor?
Yeah, so people have tried this. And in particular, there's some communities that really keep doing this. In particular, many measurements based on the Subaru telescope. But the problem with detection by weak lensing is that you measure everything along the line of sight. So while it is true that if you have a massive cluster along line of sight, you will have a shear peak. That can also happen if you just have a massive filament along the line of sight. And so if you go away from just the high signal to noise weak lensing peaks to a bit below that, then you actually get a mix of true virialized halos to things which are just projected along the line of sight. So to do cosmology with a halo mass function using weak lensing detected clusters is actually, it's even harder than selecting them by galaxies. So this is not the thing. However, there's actually a lot of information in these filaments. And so from my perspective, the field of doing cluster count cosmology with weak lensing detected clusters has moved into a different field, which is shear peak statistics. So that's literally, we take the sky map and we identify shear peaks. So, circles on the sky, which have the tangential alignment. Right. And that traces the large scale structure in a similar way to say cosmic shear, but slightly different. And so that actually is one of the higher order probes. It's not part of the 3x2 point, but there are people working on trying to do cosmology with shear peaks. It becomes a bit difficult because technically in the MC-MC chain at every step, you would need to rerun the cosmological simulation and count shear peaks, right? And so that's computationally not tractable. However, people now use machine learning to just skip the whole simulation step and predict summary statistics based on cosmological parameters. So there is an avenue that this could become relevant for both Euclid and LSST.
Okay, well, look, thank you very much. We're in for a very interesting future when all this data comes. I don't see any more questions, so I think we must wrap up now because it's 5 minutes past the time. Before we thank Anja, I'd like to make an announcement of next week's colloquium. That's it. So next week we're welcoming Jim Drake, who is one of the most informed experts on plasma physics, a physicist as well as an astrophysicist. And he's going to tell us some quite exciting things about how the solar wind is formed based on measurements from the Parker probe. So, oh yeah, it is actually still on. So that's going to be exciting. Please do come along for that. And so I think one more announcement is that there will be a dinner tonight, starting at 6:30. at the Hemingway's restaurant. So please come along. Joachim Wamskans is organizing that. So just, if you want to come along, just drop him a note. So just remains, thank you very much for it's a privilege for us to hear this, so to say, from the middle of everything what's going on, and it is very, very exciting to see this. Thank you very much, Anja.